Well, let's tinker with some exponents here. Remember how they work, and then make things more complicated by adding in fractions in our exponents. Quick review. This rule here is the big one. If you have a base to a power times that same base to a different power, the net result is that base to the sum of the two powers. So for example, 5 squared times 5 to the negative 6, we could calculate that as 5 with a total exponent of 2 plus negative 6, which is 5 to the negative 4. Oh, that went off the screen already. There we go. That's what I get for preparing these sheets ahead of time, huh? Now, what the heck does that negative exponent mean? Well, let's take that to the next rule. This is the reciprocal relationship where a negative exponent indicates 1 over the base with the corresponding exponent with the changed sign. That's a mouthful. In other words, 5 to the negative 4 is 1 over 5 to the 4. That'd be a very, very tiny number. This rule works whether the a itself is positive or negative. If you do a reciprocal action, you just change the sign of the exponent, regardless of whether it was positive or negative to begin with. Combining these two things can allow us to do quotients, so a base to a power divided by that same base to a different power. We could think of that as an intermediate step where we take 1 over b to the c and write it as b to the negative c using the property right above, and then add those two exponents, a plus negative c, which is just a minus c. Or you can go directly from here to here, and just remember, when you're multiplying, you add exponents. When you're dividing, you subtract exponents. But this isn't really a new rule, it's just a combination of the two above it. But anyway, down here is an example. 3 squared divided by 3 to the negative 4 is 3 raised to the 2 minus negative 4, which is 3 to the 6th altogether. And just for funsies and to practice with the reciprocal action, I could write that as 1 over 3 to the negative 6. We normally wouldn't write it like that because we don't like negative exponents in the denominator, but the fact is that this relationship is true. If we start with this exponent structure and do a reciprocal action, we change the sign of the exponent. Here's a rule about nested exponents: a base raised to a power and then that quantity in turn raised to another power. The net result is that you multiply the exponents together. And then here is where now we start introducing some fractions into our exponents, and this is just a visual relationship that ties us between an exponent represented as a fraction and the corresponding root of that particular number. The really common one here is that an exponent of 1/2 is the square root of that number, but this extends to anything else. B to the 1 over 5 is the 5th root of that base, and so on. And if we put these two things together, we can come up with one more example while I shift the page a little bit, because again, I got myself in trouble by preparing it in advance. The number 5 raised to the 3/2. What are other ways we can represent that? Well, we could call it 5 cubed raised to the 1/2. See how we're kind of going back and forth between the fraction itself and decoupling the fraction and using this property. This would then be the square root of 5 cubed, which is the square root of 125. Whether this version or this version or this version is the best version, I don't know. That's up to you to decide, or instructions. The other way we could decouple this number is to, instead of writing it as 5 cubed raised to the 1/2, we could write it as 5 to the 1/2 cubed. The net exponent, according to this property, is still 3/2, so it's still the same number, but it's going to be organized a slightly different way, like that. And then again, all these things are the same number, so there's a whole circle of different representations for this number. Again, beauty is in the eye of the beholder. Which one is best depends on what kind of problem you're trying to solve.